Hello, everyone. Thank you very much for joining. I'll be talking about range-based text formatting. And that's basically, we have a range library now with for C++20, but we haven't really integrated text formatting. And I'll be talking about how this could be done. Now, first of all, of course, text formatting is everywhere. And there have been numerous libraries and approaches to this problem of text formatting. And here is yet another one. And I'm sure you know this comic. And it's really hits the nail on the head in this case. So what do we have when we talk about text formatting? We have some components of text. And we have some order of these components that we want to concatenate. And then for each one of these components, we have some conversion parameters. So some components may be just plain strings that we can take them, we can take them as they are. But if you want to print a number, you may want to specify how you deal with decimal places, for example, what you use as a decimal separator. And the output is really a string after you concatenated everything. And that really describes it. That's pretty much it. Now, there are various options on how to describe these components, and I want to list them here so we kind of know what the problem space is, the solution space is for this particular problem. A popular one, of course, is a format string that was originally introduced with printf, where you just input these percent characters, percent symbols. And then you have all the other components that are these replacements are replaced with after the printf in a variadic form. It's not really type safe, so that's certainly not the favorite way how to do things, but it still, I think, influences how people think about text formatting today. There are various type safe there are type-safe versions, essentially, of printf, like Upsal, for example, has one. And of course, now there is the C++20 std format, which doesn't quite use the printf syntax. It uses the Python syntax. And but it also uses basically a text with placeholders, and then you are replacing these placeholders with additional parameters. Now, alternatively, there is what I would call just C++ way of doing it. You don't really have a format string. You just have functions and parameters and some operators to put these functions together. One example were the IO streams. They are not particularly popular anymore, but they do follow this paradigm. So they overloaded the shift operator in order to put together strings. But also plain string concatenation falls into this category of just using just C++. Now, that starts with the format strings. So what are the advantages? The advantages of using format strings are that you can kind of look at the format string and look and see what the resulting string would look like. It's much more similar to what the output would look like. And you can more easily decide on the format string at runtime. Until very recently, when you decided when you picked format strings as the way to do text formatting, you couldn't do compile time format checks but with const.expr that went away. You can now do compile time format checks, but obviously only if that format string is known at compile time. If you have a format string that's dynamic, you can't do any checks at compile time. You may get something like an exception at runtime. Now, the disadvantage is that if you're using a dynamic format string in particular, you must remember to escape it. There's been many mistakes made because someone stuck a dynamically generated format string into one of these functions, and well, surprise happened, or at best and at worst, you got a security hole. So that format string must specify some sort of escaping. And it's also not so clear how you add these parameters that you want for specifying how to print, say, a number, how you specify them. You are usually it's part of the format string that you can augment your placeholders with some syntax. So you say, like, how many decimal places you want. But it's a bit weird in my eyes because you're really using you're defining an extra language on top of C++, and you already have C++. C++ has functions, and you can give it parameters. So why do we have to create a new syntax for doing these things? Probably more seriously is that when you are defining how to format user-defined types, so you're not happy with the formatting, say, numbers, but you have your own data type that you want to format in a placeholder, then you have to define some sort of parser. It's quite elaborate to generate one of these some new to introduce some new type into that world of the format string. Now, here's another grief I have with format strings. If there is essentially no gradual change from string concatenation to the format string. So probably if someone would write code to concatenate two strings, you would just write string 1 plus string 2, right? So easy enough. So there you are plainly in the string concatenation world. Well, what now if you want to introduce a number in between these two strings? You essentially have to change your syntax. You just have to say, okay, we're not going to do string concatenation anymore, but we now go to a format string where you have 3 placeholders, and then you introduce these 3 things, the 3 parameters, in addition to insert them into the placeholders. And this discontinuity in syntax is often a problem, because once people start doing it one way with string concatenation, and then they change the code, they tend to stick with what they have. And so you got these awkward things where in some places in the code, people started off with format strings, and so they have format strings. And some places, they maybe started off with plain concatenation, and then they were too lazy to change it to format strings later on. And that's not nice. It would be nicer to have something that is basically that encompasses all these cases in a more gradual fashion, where you can easily introduce inserting format strings, or inserting like numbers and other data types, except for other than strings. One important aspect is internationalization. Very often, if you're writing a serious piece of code, of course you have to internationalize it. You have to translate the strings, and that translation is often outsourced to agencies because, well, we don't all speak all the languages, so you need to turn to experts that do the translation. Now, they are usually set up to deal with text, not code. You give them in a format like XLIF, that's an XML format for translations. You give them the strings to translate, and they will send you back the result for any particular language. And there's basically some table that you then include into your program that goes from the untranslated string to the translated string. Now, of course, these texts may contain placeholders. So there are some places in the text where you want to introduce, say, a name, right? And so you would naturally introduce a placeholder there. So in this case, you really have to use format strings. Downside is the validation, the compile time validation of format strings is really not that useful in practice, because if you have a translation, you don't always have it. Sometimes the string goes to the operating system, for example, and then, of course, you can do compile time strings. But very often, if you actually print strings for the user, this string will be dynamic because it will be translated, and you have to basically decide at runtime, okay, what's my current user language, and pick your placeholder string accordingly. Now, the thing is, if you're using, so you can't avoid giving these agencies our text to translate, but you only want to give the agency as much control as necessary for that to work with, because you don't want them to interfere with the operation of your program more than necessary. Practically, that means that really the agency will specify the place where things appear. So you only want really the placement of these components to be part of the format string. You don't want the actual formatting parameters like a decimal separator or number of decimal places or even the date format. You don't want that to be part of the string that you send to the translators, because very often you get that somewhere else from the operating system. For example, in Windows, you can set your date separator, you can set your date format, you can set the decimal separator. All these things are specified by the user in some dialogues. It's similar on Mac, and you want to use these settings. You don't want to rely on the translator to make that decision, really. The other thing is that it's in particular for the number of decimal places, it's quite often it doesn't depend on the language, how many decimal places you have. It depends, say, on the usage. If you have yen, you may not have any decimal places, while if you have US dollars, you usually have 2 decimal places. So it really depends there on the currency rather than on the language or that you're currently in, or on the regional settings. Now, let's look at the other choice. That's the just C++ choice, and see how that goes. The most common way to do it would be IO streams. They're not particularly popular, and because they abuse operator overloading, presumably because they didn't have any variadic templates back then. They're also bad because they are stateful, so you can switch around the state while you pipe these sequences. You shift these sequences of placeholders into your stream. So you really have to be careful that you're on the right state, that you're not setting the precision to something in one place of the program and then reset it to something else in a different place of the program. And back when many years ago, when we still used IO streams, that was a real problem. They're relatively slow because of virtual calls, and they always introduce an extra copy when you go from the string stream, when you generated your string into the string stream, and then you want to get the string out of it. So that's not particularly nice either. Now, the alternative to IO streams is something very simple, which is just simple plain string concatenation, right? We know how to concatenate strings in C++, and you can basically just concatenate strings. It still abuse operator overloading a little bit with plus, and by default, just out of the box, there's no real formatting options, and it's also relatively slow. It's not a whole lot better in that regard than IO streams, because you're going to generate many temporaries, right? For every snippet that you want to introduce into your string, you're going to generate a separate temporary string and then append it. And that means many heap allocations, which is not nice. That said, I do like that concept because it's really the essence of formatting. It reduces the formatting into very basic things. At the end, it's just concatenating snippets. And then the question is, okay, how do you turn some data type that you have into a snippet that you can then concatenate? And that's kind of a separate problem, right? So you turn your data type into a string, and then you concatenate these pieces of strings together. It's very naturally extends to anything that's user defined. If you want to format something special, something where you want to control it, when you introduce a new type that is supposed to be turned into a string, you can simply call a function that returns a string. It's very natural, right? So you're just putting the string together with whatever means necessary, and then you return it. So the idea for this talk is going to be to take all these strengths of string concatenation, the things that I like, but eliminate all the things that are bad. So in particular, the performance, and make that basically competitive with hand-generated, hand-rolled loops for formatting. And the way we're going to do this is with ranges. I'm sure by now many of you know the range-based for loop, right? That's the first thing that was introduced that used ranges in the C++ language. But now, of course, with C++20, there are also Eric Niebler's ranges in the language, and I highly recommend using them because it really makes for a different coding. If you use ranges, we use them everywhere. Now, there is a more extensive version of the C++20 ranges in Eric Niebler's library that he has on GitHub. Now, here are these are the old versions where basically that's where ranges started. There was a boost range library. It's pretty much deprecated by now, but it's still around. And it really introduced me, at least, to the whole concept. We do have our library, so all on GitHub as well, if you want to use it. It does change quite a bit over time, but if I would start coding, I would probably take it at least and as a starting point. And also what I'm showing you here is also part of the library. Now, here's the essence of ranges. So usually you would find in the old days, right, you would write something like std find, and you'd have to specify 2 iterators. And the insight is, well, these 2 iterators really always belong together. And why not put it into one object and then just call that a range, and instead of having pass 2 things, we just use one thing and pass that. And the ranges library in the standard library contains a lot of wrappers around the other algorithms, the old algorithms that took iterators, where you can now pass ranges. And a range is really anything that has a begin and an end, right? Where you can basically get the 2 iterators out. That contains, or these things encompass containers, and they own their elements. That's like the vector and the basic string, but also what the standard library calls views, and they just reference their elements. It's essentially really an iterator pair wrapped into this single object. And both these things can be used wherever a range is expected. A special thing that's kind of goes beyond this whole iterator idea is that ranges may do calculations. They may do things on the fly while you are iterating over them. So in the standard library with this pipe syntax, you can have a range and filter it according to a predicate. And when you're writing such an expression, then nothing will happen. There's no work being done immediately. Just the range and the predicate are being captured, and only when you then start iterating over the elements, then it will skip the elements that don't pass the filter. Now, why do I think I know something about ranges? As I already said, ThinkCell has its own range library, and we learned a lot from Boost Range developing it. It's, I think, more powerful than the standard range library. It goes beyond the standard range library. We have about 1 million lines of production code that uses that library. And we are very lucky that we don't have this typical chicken and egg problem of library design, where if you have a library that you just developed and it doesn't have any usage, you're not going to really be able to validate your design because you don't have any users. And it's really hard to design something where you don't have any or lots of examples of how it's being used. Now, the other thing is, if you have lots of users and many people rely on your library already, and you get a lot of information of what you've done right and what you've done wrong, then it's really hard to change the design because everyone's going to scream because they have to change their code. Now, at ThinkCell, we are lucky because we have all this code in-house that's using the library, and we actually have extra resources. We have a developer that does nothing else but refactoring. So whenever we change something in the library, he will change whatever is necessary to be changed in the code. So we are really free to change the design of our library, of the range library, and find out what's good and what's bad and how we optimize it. And this tweaking of the library is going on to this day. It's still not finished, and it's still being improved. Now, so here's here's the basic idea. If we want to use ranges for text, the first thing that we would probably like to do is all these special case member functions of basic string that kind of replicate what the standard library already offers, we would write with range functions. Right? So instead of calling string find, you would go to the range find, which really does something very similar, and it spits out an iterator instead of an index. But it's very, the nice thing about it is that you don't really care so much anymore whether you have a sequence of characters or you have a sequence of other things that you want to do the finding in. It's pretty much, you're just going to use the same functions for any kind of ranges, whether it's characters or not. And you are also very flexible with string types. Even if you have like an operating system, a library-specific string, then it's usually pretty simple to wrap it into a range interface, basically just by implementing and it could be a freestanding function object and end that gets suitable probably pointers or iterators out of that object, and then you can iterate over it, and then suddenly it's a range, and you can use all the range functions with it. So this whole, and I know this is often a matter of debate about, okay, which string type are we going to use, and are we going to use the basic string, or are we going to Qt brings its own string type and everyone brings their own string type. Now with ranges, suddenly you don't care so much anymore. You can just use whatever your external environment likes to have as a string type, and internally the code is pretty much the same. Now, unfortunately, the standard library designers haven't been quite so aggressive in pushing for ranges for string processing. C++17, for example, brought us the basic string view, which really just perpetuates this basic string member interface, this old member interface. And of course, it was meant to be a drop-in replacement for basic string, because people were just passing around basic strings by value everywhere, or if they had to cut out a piece of a basic string, they would just generate another basic string, which just heap allocation, that was all very inefficient. So basic string view was designed to solve this problem, and it does, but it's just not getting people into this new world of ranges. Now, how will we go about using text formatting for ranges? Now, of course, any suitable range libraries already have concatenation, so that you can do a concat of two ranges, and these ranges could be strings. They're in a range v3. I wrote it here in the think style syntax. You would write tc concat, and there's also a concat in range v3. I don't think we have it yet in C++20, but I'm sure it's going to come very soon. Now, if you want to now introduce some data, if you want to format some data, it would be quite straightforward to introduce formatting functions. Let's say we have one that is like an asdec, and so that as a decimal, that turns any number you give it, for example, a double, into a little snippet, a little string with 2 decimal places. So here we have indeed this asdec in our library, and you can write it like that. So there you have a range that has you $1 something. Now, keep in mind with this design, it's not like IOStream. Double itself, when you just insert it, is not a character range, because, well, double is not a range, right? And you really want to be clear, even if you're doing by and large concepts or duck typing, and everything is very generic, but we still have to be clear of what the semantics are of what we are talking about. And a double is just a number. It's not a string. And it doesn't even mean, it doesn't have the semantics of a string. So that's why there is this extra formatting function that tells you basically how to turn that double into a string. And I mean, maybe with doubles, maybe less likely, but with integers, maybe you don't want to have it as a decimal. Maybe you want to have it as a hexadecimal or an octal, and you can express it that way very easily. And if you do it like this, there's really no need for a special format function. We don't have format anymore. We don't have, there's no printf, there's no std format. It's just, we're just concatenating snippets of string of ranges. Again, extension of this approach is very simple. If you want to say print dollars always with dollars appended, the dollars word appended to it, you can do this very easily by just providing a function that returns a concatenated string. or concatenated range. So in this case, the dollars functions concatenates the sdeq with the string and returns that, and then you can use that or call that function in your concatenated strings elsewhere. And again, you can print the dollars with dollars appended to it. Now, to be clear, all the range algorithms will work. So you can do a for each, and then you get of sdeq, for example, and you would get the individual characters of this printed double. Now, algorithms like all of any of, they all work as well. It's just a range. You can any tool that you want to use will just work. Now, eventually, after we constructed these ranges, they will probably have to end up in some sort of container, so we can actually pass them, say, to the operating system for printing. And how would we want to do that? How can we design? How should this look like? Well, the std string already gives us empty construction, right? So if you just default construct a string, it's empty. Now, there is also construction from literals, which are strings, so semantically strings, or another basic string type that also works. Now, it would be very nice if we could also construct the string from a range of characters. And I think if we are going to evolve the standard library for a little bit longer, this is going to be possible, at least with the std ranges, with the standard ranges we have in the standard. For now, we're just going to say, okay, conceptually, this is what we would like. We would like to take a range and turn it into a string. And that should really work for single strings, but also for concatenated constructions like what we had. Now, if you're already talking about these concatenations, maybe we could shorten things a little bit by just saying, well, if we have multiple arguments to the string constructor, then it would be nice if that would essentially mean concatenation. Just by extension, because without any parameters, we get an empty string. With one parameter, we get that string. Well, what are we going to get with two parameters? Well, maybe we get the two strings concatenated. There's not a whole lot of things you could do else if you construct a string. Now, of course, what about these existing constructors, right? So here I wrote these constructors of std string. They all compile, right? But what do we do about them? Well, first of all, let's look about what they do, okay? So the first one is actually undefined behavior, because we are using the first 3 characters of A, and that's beyond the size of A, so you get a buffer overrun. That's not good. Well, the second one adds 65 times Control-C. I'm sure you are immediately aware when you see that's going to be the case, because the A is really the count and the 3 is the character. Only the third one does what you probably expect, and it adds 3 times an A. So my argument would be, we don't need these constructors. They are just more confusing than it's worth. And they're easily encapsulated by something that is much more telling. You could say, well, can't we create a range, and we have a range function like repeat n that takes a single element and then the number of times that element is repeated. And repeat n, in fact, is in the thinkstyle library. It's also in range v3, so it's going to be in the standard library as well. And I think if you want 3 A's in a string, it would be very natural to construct it to say, first, basically semantically, I want to have something that repeats a single character for a certain number of times, and then I'm turning that into a string. So that's much clearer. Now, since we can't use constructors, we can't change constructors in the standard library. Our library does a little workaround and says we introduced an explicit cast, which we kind of use throughout the library everywhere when we have to construct things, which has the advantage that there we can really simulate and add, removing the explicit constructors that we would like to add or remove from a type, but we can't because of it's the standard and we can't change it, right? So here, this is kind of our stand-in for we want to have a constructor, and there you can do all these things that I described. Now, with this explicit cast is also used in other places where we have to construct elements, we have to construct objects. There is a wrapper, for example, for mplaceback in the library, where you can just pass in a string. You can pass in something that constructs into a string. So you can here we have a vector of string, and you can actually do an mplaceback on that vector and pass in a range. And that in that case it's sdeq, and that sdeq would actually be formatted into a std string. It would convert into a std string when it's actually pushed into the vector. And cont mplaceback basically takes care of that, and using explicit cast as a little helper. And of course, you can also append to a string, right? So, and there the same is true. You can append a single argument that could be a concat, or you can just omit the concat. And if you have multiple arguments, they just get appended one after the other. Now, as I already said, we need placeholders because we want to do translation. And we do have placeholders in the library as well. You can use it with the Python syntax, so with basically numbered placeholders, and then the parameters that you give to the placeholder function, they are really just strings. They are really semantically just or ranges. So really the only purpose that this placeholder function serves is that it puts these strings that follow after the placeholder function into the respective place of your format string. So it's purely a positioning thing. It doesn't do any formatting per se. That doesn't parameterize any formatting. You cannot specify the number of decimal places. That's something you have to do when you create the string, and that fulfills that requirement that we don't want to give too much leeway to the translation agencies and to mess with our program. Now, there are also named arguments. They work like this. There you are in curly braces. You put the parameter names, and then you can pass some named arguments. And here we've, for example, format also the time as ISO 8601. That's just another formatter that you can use for that spits out the 8601 date and time format. Now, how do we implement the whole thing? So I kind of describe what we want, and I like it, and you be the judge. I just popped up the open question and answer session here. If you have any questions, just ask them, and I'll answer them as I go. I'll glance at this window once in a while. So again, how would you implement it? The very naive implementation would be that each formatter returns a std string, and then the concat again returns a string, and then the append appends strings. So you have strings everywhere, and that's probably not terribly efficient. So it's simple, but you have to allocate and copy many strings. And the other thing is I'd be done talking. So since I want to talk some more, I will explain to you how we implemented this functionality. Now, first of all, we want to avoid heap allocations when you're generating these strings. At best, we want to have a single heap allocation at the very end when we have to put all that big concatenated expression into a string, into a container. So the idea would be that we make these formatters lazy, because I mean ranges can be lazy, like we've seen with the format with the filter, and we will make these formatters lazy as well. They will just capture the content. They will just say capture the number that you want to print, and the actual printing, the actual turning into a string will happen when you are iterating over that range. And a good thing is that the size of these formatter objects is known at compile time. They just capture whatever you give to them, and you don't need any heap allocation typically. You can just store them on the stack. Now, this is how it would look like in practice. You are this is the example with the dollars again. So this dollar function here would you have an sdeck, and this sdeck really stores just f, like the double that you passed, and 2, and the concat stores just the components that you give to it. It will store any L values you give to it by reference. For example, well, the dollars, the literal is an L value reference, so it will be stored by reference. While the R values that you pass to it, for example, the result of the sdeck, will be stored by copy. It's a bit like expression templates if you are familiar with them. And after you build basically this expression tree, it gets returned. And then only when you are then doing the explicit cast to the std string, that whole tree will get unfolded and gets iterated over and spits out all the elements or the characters that it needs to be printed. Now, how can we make this fast to do this formatting into containers? First of all, it's the fastest way to do this would be we first look at the string length, determine the string length, then we allocate the whole memory of the whole string at once, and then we just fill in the characters as quickly as possible. That's basically the idea. So how can we do this? Well, the first idea would be, what if you have inside our explicit cast that goes to string, or in general to a container, we would have some container constructor that pulls the 2 iterators out of the range and sticks them into the container constructor. So it would look like this, really. And this is just the explicit cast implementation for containers. There could be many more for non-containers. I just left out the enable if and concepts and so on. Now, the problem is that these formatters are often not random access. So the sdeck, for example, will print out the characters of a number one by one, but it's hard for it to say jump to the 5th character, right? So that's not going to be so easy. And in that case, the standard string constructor actually runs twice over the range. It wants to first find its size, so then it runs over it once if it's not a random access range, and then again to actually generate the characters and copy them into the string. That's not ideal. We have to see whether we can do better. Now, if the range actually has a size member, we can take advantage of that. So if we have little enable if range has a size and it's not random access, well, if it's random access, you can easily implement a size. But if it's not a random access, but it has a size, then we can just iterate first of reserve memory inside the container, and then just iterate once over the range and place back the elements. So that's likely more efficient than running over the range twice, in particular if calculating the range is non-trivial, which may be very much the case for range formatters, or for string formatters. Now, there is also a TC append that works accordingly. It does a reserve and then iterates. Now, I put in a little pitfall here for you to find. You can take a look what's wrong about this piece of code. And I will tell you. Now, the problem here is this cont reserve. Whenever you use cont reserve, and then that may be the lesson of the day, be very careful about this. Because if the container doesn't start off empty, it's not fully constructed, but it already has some size, there's always the danger that cont reserve only reserves exactly the amount of space that you specify. Now, if you advertently or not, more likely inadvertently, run this reserve in a loop where repeatedly you extend the strings by a small number of characters, then this will become very inefficient because you get very many reallocations, because every reserve will just reserve as much memory as necessary. I think that's a design mistake because it's just too easy to pessimize your code that way. A better cont reserve is probably one where you say, well, if your capacity is not large enough and you want to reserve more, then at least make sure that you are growing the container by a constant factor over its present size. So your amortized are always guaranteed to get no more than a linear number of reallocations and copies of elements. So if we are doing this improvement of cont reserve, then we can use it in our append safely and do what we want it to do. Now, okay, let's say we have that. Now, the next problem that we will run into is that we need, with that implementation, we actually need iterators for our ranges. And as you can imagine, it's not necessarily the fastest way of doing things. And I'll give you an example of here where iterators are really, well, at least not as efficient as they could be. Let's take the concat, which will be used a lot in our string concatenation. There, the iterator of a concat is by necessity some sort of stitch variant of the iterators of the components. So essentially, the state of the iterator has to mean in which component am I currently in, and then within the component, where am I there? And that requires that every time you do an iterator operation, you actually have to branch on the component that you're currently in. So, for example, the iterator operator ++ operation of the concat will look something like this. You do essentially a std visit, and it would need to branch on the variant type. And if you are in the first component, then you have this iterator 1, and then you increment it, and then you check for end, and then you jump your variant to the beginning of the next range. And for iterator 2, you can simply increment. But you have to do this every time you do an operator ++. You have to branch, which is inefficient. Now, the operator plus the operator star will actually look the same way. You would have the same problem. So if you dereference the iterator, even there, you also have to make the decision which component am I in, what kind of iterator do I have, so you know which operator star of which iterator to call. Now, with TCS DEC, it's actually quite similar because if you want to implement this as an iterator, the bookkeeping that's required to spit out the characters one by one, each time operator ++ operator star is being called, that also this bookkeeping also costs you performance. It would be much nicer if you could just output these characters one after the other in a single loop. And we'll see how we can improve that. Now, C++ iterators do external iteration. The consumer that wants data calls the producer and to get new data. So it will call it star it, and then you do ++ it, and then you star it. And every time you're calling the consumer that takes the data, calls into the producer. That means that the consumer of the data is at the bottom of the stack, and the producer is at the top of the stack. You're calling into the producer, and you're essentially calling into another call frame, another stack frame, and there you're producing an element, and you're leaving the stack frame again. So you are the producers at the top of the stack. Now, being at the top of the stack or the bottom of the stack has consequences. And if the consumer is at the bottom of the stack, you have essentially a contiguous code path for the whole range. So the whole consumption of the range is going to hang on one thread of code. That makes the consumer easier to write. And it also has better performance, because if it carries any state, that state can be encoded in the instruction pointer. It's essentially your state is in which part of the program am I currently in. And you can allocate limitless amount of memory pretty much on the stack until your stack overflows. So there's no strict limit. Now, if the producer is at the top of the stack, then, as we already seen, there is only a contiguous code path for each individual item. Each time you call star it, you'll get another piece of data, and then you are leaving your operator star function, and next time around you have to restart again. You have another, you have the same entrance point, and you have to restore your state. That makes them harder to write, and you get worse performance. You have the single entry point, and you have to restore the state to whatever it was before. You have to remember, you have to do the bookkeeping. And you also, in between iterator calls, you only have a fixed amount of memory that you can store inside your iterator, or you have to allocate things on the heap. Now, what's the alternative? We can turn the whole thing around. Here, we had the consumer at the bottom of the stack and the producer at the top of the stack. Now, we can turn the whole thing around and say, why not put the producer at the bottom of the stack and the consumer to the top of the stack? So, and that actually makes formatting text much more efficient. And it's called internal iteration if we do this swap. So producer at the bottom, consumer at the top. Now, what does that mean? That means essentially the producer prepares a piece of data, and then it calls the consumer to consume that piece of data. And then the consumer returns, and the producer is again preparing the next piece of data. Now, the producer is at the bottom of the stack. It has all the advantages of being at the bottom of the stack, and the consumer is at the top and has all the disadvantages of being at the top. Now, this has been done many times. It's kind of called the visitor pattern or whatever, or internal iteration. In essence, it's always the same. It's really about reversing the order of consumer and producer. Now, the nice thing is that many of the range algorithms that we have implemented for iterators, we can also implement for internal iteration. Now, some of them you can't. So if you need iterators like a binary search, that's kind of hard to do if you do internal iteration, or you want to find that if you want to return the iterator to whatever you found, that you can't do with internal iteration. But if you only need the value, then internal iteration is really just fine. Many other things you can implement without any problems with internal iteration. For each, which is probably the most frequent range algorithm, is by itself exactly like the essence of internal iteration. You call a lambda with or a function with each item, so that can easily be put at the top of the stack. Now, accumulate, all of, any of, none of, they all can be implemented in terms of for each, so they all have no problems with internal iteration. Now, I talked about that ranges can do these lazy computations. They can filter things on the fly, for example, and that you can also do without problems with internal iteration. It can actually be more efficient with internal iteration. Same for transforming elements on the fly. So when you're iterating, you get a transformed version of your actual data. So it is quite attractive to say we just extend the range concept to internal iteration. Now, the ranges implement the operator parentheses, and that takes the sync functor. So the operator parentheses is already used for std span, so we have to kind of exclude it. But now we can actually write our ranges as lambdas. We can have a for each, and it takes a sync and calls the sync with two elements. So this first lambda on the for each is really just a range. Now, and the for each has some internal logic that uses the internal iteration if available. Otherwise, it uses iterators. Now, this is now what concat looks like with internal iteration. You have a for each, and that for each is just calling in turn for each range that it contains, that the concat is concatenating. It turns it just runs for each again. So it's really just as efficient as it could be. Now, so what we can now do is we can introduce an appender sync for explicit cast, so that we can append using for each, because for each is our way to do internal iteration. And appender is really the customization point that defines how the sync looks like to append things to a container. Now, the default for std containers is probably just going to be an emplace back, if you have it here at the bottom. But we can customize it. We can make it more efficient. One way or one reason we want to make it more efficient is the reserve that we had. And for that, for doing a proper reserve, the sink really needs the whole range to call std size. We want to call std size on the whole range prior to starting the iteration. Well, you can do this by having another customization point in the sink. So the sink, which is the thing that usually the elements are being passed to and they're appended to whatever container you have, may contain another element, another member function called chunk. And if that function chunk is available and is willing to take the range, the whole range is passed to it. And now it can do whatever it wants. It can find out, oh, does my range have a size? And then I'm reserving whatever memory I need. And then I can basically call the original for each, but I know now that I already have enough memory reserved. Now, file sinks are another place where we could actually use that customization point chunk. So if you have an appender to a file that's not appending to a piece of memory, but it directly writes into a file, it can actually take anything that is convertible to a std span. If you already have a contiguous memory chunk, then you can write that contiguous memory chunk to the file in one go. And only if you don't have that, then you have to go character by character. Now, at the end, I just have a bit of performance comparison. How fast is our range library compared to, say, handwritten code? And I gave it deliberately a trivial formatting task to format 10 A's, 10 B's, and 10 C's. And it's deliberately very simple because that would best expose any overhead we have in the implementation. And the most trivial way to do this would basically be an unrolled loop, and this is basically our straw man. You just have a buffer. The buffer is a fixed buffer. It doesn't do any allocation, and you have a handwritten loop that just writes 10 A's, 10 B's, 10 C's into that buffer, and that's probably the very fastest way you can do this. And the compiler can easily do any optimization it likes. Now let's compare that to an actual appender. So you again have an appender that is that fixed buffer appender, and we want to leave out the memory allocations for now. And you just then write a tc append with buffer, and you use the repeat n range function, range formatter that repeats a particular character n times. And so this is basically how we write it with ranges. It's much more readable, much nicer. But how does the performance compare? Well, actually, if we do this with iterators, we lose about 50% more time, 50% speed. So it takes 50% longer than the handwritten loops. Now, if we do this with internal iteration, we actually only lose 15%. So really, the whole building the expression tree and then iterating over the expression tree, it doesn't cost you much, and you can write really nice code, and it's just as efficient as it could be. And this is, remember, this test is the worst case because the actual complexity of the formatting itself, the repeating the character n times, is really the worst case. It's very simple, and anything that would do substantially more work would produce even smaller differences in performance. Now, let's see what we can do with a basic string. Can we make basic string more efficient? So let's have and we don't have that yet in the library. It was just to explore what kind of performance improvements are possible. Let's say we have a toy basic string implementation where we only have heap pointers, begin, end, and end of memory. That's how very frequently the vector is implemented. Basic strings often have an internal buffer, but we'll leave this out for now. And we again have this trivial formatting task, and we put that into our basic string. Now, if we do this with a standard appender, then we would do the cont reserve in the very beginning, and then we would, for each individual character, the appender would do an mplace back on that container. Now, you'd say, well, we reserve all the memory, that's good, and then we do the mplace back. So what kind of performance do we get? Well, the question is, can we do this better? Can we improve performance? And actually, it turns out, yes, we can, because what's happening here is that the mplace back would check each and every time it does an mplace whether it needs to reserve, whether it needs to reserve more memory, whether it needs to reallocate. And we know already, because we reallocated in the beginning with the cont reserve, we know already that that's not necessary. So we could actually optimize that check and make it more efficient. Now, here's what we get. So the string was only 30 characters, and we used the actual heap allocation of the operating system. And so we would say a heap allocation, and we only did one in both examples. We only did a single heap allocation. And you would say, well, how much can we really save with 30 characters? Well, turns out, if we don't do the end check, we can still save 20% less time. That, of course, in order to exploit that, we would need our basic string implementation, which we don't have yet, or have to have some way for basic string or std vector, if you want to format into a vector, to expose the individual, expose the buffer, the internal buffer. All right. Here are some future work we could do with performance. Now, we always check the size in the beginning to do the reallocation. Maybe some of the pieces of our concat don't support size, and then we can't do size for the whole concatenation. Well, we could say we implement a customization point, say min size, that just calculates a lower bound. It's essentially the sum of the min size of the components, and you can always return 0. So you would basically calculate, well, what's the least number of characters I will definitely need, and you can already do the allocation for them, so you don't have to repeatedly reallocate. Now, the opposite could make good use of a max size. Say you are putting your data into some sort of I/O buffer to write to disk, and there you usually have some fixed buffer that you fill with data, and there you have the similar situation where at the end you always have to check, am I at the end of my buffer, to basically flush the buffer and get a new one. But if you knew in advance that you are not going to overrun your buffer, then you could omit the check, and that could be done if we had the opposite customization point, max size. Both are not implemented min size or max size, but that would be future work if we further want to increase performance. All right, coming to the end, I showed you how to do range syntax and how to use range algorithms for text formatting. Now, for performance, we really need 2 new customization points, or few new customization points. We would need internal iteration, and actually the std format in the C++20 library also does internal iteration effectively under the hood. So it's really the same trick to increase performance. We would need special appenders to construct containers, and this chunk trick to get to pre-allocate the memory. And then the performance of this range text formatting is really competitive with handwritten code, and I think it produces nice expressive code if you use it. Now the whole library is on GitHub here, and it's now also under the Boost license, so you can use it freely in even commercial projects, not a problem. Well, if you want to help developing the library or do something else, here's the link to our hiring page. All right, thank you very much. And if there are any questions, I think we will switch over now to the other website, and I'll take discussions, questions there. Yeah, hope to see you over there. And I'll switch over. So if you want to discuss, I'll meet you there. Bye.